Have you ever noticed that when you push an object, the object changes its position? This is called motion. My name is Gandon Christian. Welcome to another exciting class in physics. Our theme for today is conservation principles. And our topic is linear momentum part 2. By the end of this lesson, you should be able to solve simple problems based on Newton's laws of motion and the principle of momentum. Whenever there is a change of position of an object due to a force acting on it, we can say that object is in motion. The force acting on the object changes its position, distance, and direction. This force also changes its momentum. This force I'm talking about is stated in Newton's laws of motion. Just like in our previous lesson, impulse and momentum are also applied in one of Newton's laws of motion. Let's go on as we look at these laws. Newton's laws of motion are 3 laws that best describes and investigates the motion of an object, its physical property, both in physics and in nature. These laws describe the relationship between an object, the force acting on it, and the way the object responds to the force acting on it. This force could be a pull or push. These laws were first compiled by Sir Isaac Newton in 1687. The first law explains the action of the force. The second law measures the action of the force. And the third law specifies the action of the force. Now let's look at these laws one after the other. The first law states that an object will remain in a state of rest, all in uniform motion, unless compelled by an external force to change its position. This means that an object will remain at a place or continue moving unless you push it or pull it. This law is also called the law of inertia. For example, if you keep a notebook on the desk, it will remain there for as long as you don't touch it. Also, while driving, if you don't increase the speed of the car will remain at the same speed because there is no external force to change it. From this image, you can see the ball. Unless the boy kicks the ball will remain at a particular spot. The second image shows that the object is at a place. But when a force is applied, the object moves in a direction. The third image shows that this object is at a place. But if a force is applied on it, it will certainly change its direction and move in the direction of the force. This is what Newton's first law of motion states, that an object will remain in motion or at rest unless compelled by an external force to change its position. Here we have Newton's second law of motion. The Newton's second law of motion states that the rate of change of momentum is directly proportional to the applied force, and it takes place in the direction of the force. Remember in our previous lesson, I told you that momentum is simply mass in motion. So when this object changes its position as a result of a force acting on it, the object definitely must move in the direction of the force. This means that the larger the mass of an object, the more it will be difficult to move it. For example, let's say you have a car and a truck, and you're asked to push them at same speed or at same time. You observe that the truck will be difficult to move because the mass is greater, while the car will be easy to move because the mass is lesser. So in Newton's second law of motion, the larger the mass of an object, the more force is required to move it. Let's see this image. You can see from this image, a force is required to move the object in a certain speed or direction, which is mass times acceleration. You can say the boy is trying to push the car. If the mass of the car M is greater than the force of the boy will find it difficult to push the car. But if the force of the boy is greater than the mass of the car, definitely the car will move in the direction of the force. Now, here are some properties of Newton's second law of motion. 1. The impulse applied to an object is proportional to the force within a time interval. This means that time is required. 2. The greater the force applied to an object, the greater the impulse within a time interval. Also, time is required. And lastly, the greater the time interval, the greater the impulse. You can also see time is involved. Now, let's look at this equation to explain further some of the properties of Newton's second law of motion. You can see impulse is simply force multiplied by time. The change in time simply means final time minus initial time. This means when you push an object, when the object starts moving from point A and stops at point B, the time taken for that object to move from point A to point B is what we mean by change in time. So the impulsive force is simply force is equal to mass of final velocity minus mass of initial velocity all over change in time. Since we have a common coefficient, m, one is taken out. So we have mass into final velocity minus initial velocity all over change in time. So our equation is force is equal to mass into final velocity minus initial velocity all over final time minus initial time. You can see from this image, a boy kicks a ball with a force. The ball travels in a given time and creates an impulse at the goalpost. Now, let's see Newton's third law of motion. This law states that to every action, there is an equal and opposite reaction. This means that for every object that moves or collides with another, there is an action force and a reaction force. Imagine this scenario. If I give you a slap, I'm sure you will react, right? It's either you will fight back or you will feel the pain. The slap given to you is the action force, and you trying to fight back or feeling the pain is the reaction force. So you can see to every action, there is equal and opposite reaction. You can see from this image, to every action, there is an equal and opposite reaction. Now look at this other image. The man jumps up from the canoe. An action is created. The canoe jerks backward as a result of the force on it. This jerking backward of the canoe is referred to as the reaction force. Now, having discussed extensively these three laws, let's look at some mathematical examples. Example 1. A stationary ball is hit by an average force of 50 Newton for a time of 0.03 seconds. What is the impulse experienced by the body? Solution. We are given force as 50 Newton and our time t as 0.03 seconds. You remember the formula for impulse, which is force multiplied by time. So using the parameters given, our force is 50 and our time is 0.03. If you multiply both, you have 1.5 Newton second. Let's see another example. A body of mass 3 kg moves with a velocity of 10 meters per second. Calculate the momentum of the body. Solution. We are given 3 kilograms as our mass and the velocity is 10 meters per second. I'm sure you still remember the formula for momentum, which is mass times velocity. Inputting the parameters, we have our mass is 3 kilograms and our velocity is 10 meters per second. When you multiply both, we have 30 kilogram meters per second. Moving on to the next question. A 90 gram of stone is pushed along by a horizontal force of 20 Newton. A frictional force of 8 Newton opposes the motion. What is the acceleration given to the stone? Solution. Remember, we have a force of 20 Newton and 8 Newton. So what do? We subtract 8 from 20, which is 12 Newton. The given mass is 90 gram. By converting it to kilogram, we have 0.09 kilogram. You remember the formula for force, which is F is equal to ma. So, using the figures given, our force is 12, our mass is 0.9, but acceleration is not given. So, we have to find acceleration. Now, let's make acceleration the subject of the formula, which is A. By making acceleration the subject of the formula, we have acceleration is equal to 12 over 0.09, which gives us 133.3 meters per second. Then here is our last example. A body of mass 5 kg moving with a speed of 30 meters per second is suddenly hit by another body moving in the same direction, thereby changing the speed of the former body to 60 meters per second. What is the impulse received by the first body? Solution. We are given a mass of 5 kilograms. Our final velocity is 60 meters per second, and our initial velocity is 30 meters per second. Using the formula impulse Ft, we subtract the mass multiplied by the initial velocity from the mass multiplied by the final velocity. So by simplification, we have mass into final velocity minus initial velocity. Inputting the figures, remember our mass is 5 kilograms into final velocity is 60 meters per second minus initial velocity, which is 30 meters per second. Our answer is 150 newtons second. Having solved those examples, we have come to the end of the class. But before we go, let's take a quick summary of what we've learned so far. First, we learned that Newton's first law states that every object will remain in its state of rest, all in uniform motion in a straight line, unless compelled by an external force. We also learned that Newton's second law states that the rate of change of momentum is directly proportional to the applied force, and it takes place in the direction of the force. And lastly, we learned that Newton's third law states that to every action, there is an equal and opposite reaction. I'm sure those examples we solved together, you understood them properly. Now let's take some test questions. Question 1. Newton's first law of motion is also known as A. The law of inertia, B. The law of conservation of momentum, C. Vertical motion, or D. Gravity. The correct answer is A. Newton's first law of motion is also known as the law of inertia. The second question. Acceleration of an object will increase as the net force increases depending on its A. Shape, B. Mass, C. Volume, or D. Density. The correct answer is B. Mass. You remember, the larger the mass of an object, the more force is required to move it. Thank you for your time. In case you've not seen the part 1 of this lesson, ensure you do so. Till we see you again in our next class. Bye-bye.